So here is the grand finale of this lesson. Okay, the obviously everything we've done in this course is algebra, and now here's the fundamental theorem of algebra. And it may or may not be something that's really important in whatever you do, but if you become a mathematician, this is absolutely essential, and this just shows you that what an amazing thing polynomials can be, the nature of polynomials. It says every non-constant polynomial has a complex zero. That means you can write down any polynomial you want, no matter how nasty it is, no matter how big a degree it is, no matter how ugly the coefficients look. There's going to be some complex number that you can plug into that polynomial and get zero. Now, of course, this doesn't tell you how to find that polynomial. It just says that it exists. But, and its proof, there are many proofs of this theorem. They're all beautiful, and they're all beyond the scope of this course. So we won't be going over the proof of the fundamental theorem of algebra. But I do want to talk about consequences. And this first consequence, in a way, it's even more important than the fundamental theorem of algebra itself in terms of what I want you to come away with. If there's one thing that I want you to come away from this lesson, besides the introduction to complex numbers, is this. If f is a polynomial of degree n, where n is at least 1, then every polynomial of that form will have this form. A constant times x minus a number times x minus another number, and so on to x minus an nth number, where a, alpha 1, alpha 2, alpha n are not necessarily distinct complex numbers. And the reason for it is why this of course implies that alpha 1, alpha 2, alpha n are going to be the zeros, the complex zeros of f. And we see that we get that f will have, if a polynomial has degree n, we get n complex zeros, exactly n complex zeros, even though they might not be distinct. But they always have, and then it's going to be a product of these n linear factors. And we saw every polynomial that we've looked at in this lesson has been factored in this form. Okay. The reason how this works is that so f is a polynomial, it has a root, it has a zero or a root, alpha 1, let's call it. That means x minus alpha 1 is a factor. So that means f can be written as x minus alpha 1 times some polynomial g of x. And then we apply the fundamental theorem of algebra to this. G of x is going to have a root, call it alpha 2. So we can write this as x minus alpha 2 times some other polynomial, we'll call it h of x, and so on. And that's how we get this. So I want you to understand that this form is in essence what every polynomial looks like. And when you're asked to factor a polynomial over the complex numbers, this is what we mean. Factoring something over the complex numbers and finding the roots are essentially the same thing. Some other consequences we'll spend on just a little brief time amount. So as I said, a polynomial of degree n has at most n complex zeros, and actually we can even say exactly n complex zeros. Okay, if we don't care if they're distinct or not. If f is a non-constant polynomial with real coefficients and the degree is odd, then f must have a real zero, because if it had only non-real zeros, they occur in pairs. So you'd have an even number of factors here, but you can't have that. You'll see that the degree of this polynomial is equal to the number of zeros it has. So we can't just have, if an odd degree, we have to have at least one real zero. And we sort of already knew that from our end behavior of polynomial graphs. We know that if the degree is odd, the graph shoots off on the right and shoots down on the left, or vice versa. So it's going to have to cross the x-axis at some point. But here's another way of seeing that. If f is a non-constant polynomial with real coefficients, it can be written as a product of irreducible factors of degree 1 and 2. So that's basically like this. So if we factor just over the real numbers, a polynomial will look like this. Don't worry about number 4 too much. I do want to do example 7. Okay, I left this blank in your notes. You can fill this in now. I want you to find the zeros of this polynomial x to the 4th plus 8x squared plus 15, and then factor f over the complex numbers. You will see a problem like this in the homework as well as a quiz. And the way you do this is you want to basically, so first, you set this equal to 0. And you can try to factor this. You can factor this, or you can use a quadratic equation to solve for x squared. But it's probably easier. You can see that this will factor as x squared plus something times x squared plus something. And here that something is plus 3 and plus 5. Okay, if you think about that, if you multiply this out, that's what this becomes. All right, so that means either x squared plus 3 is 0, or x squared plus 5 is 0. And in this case, that means, well, x squared equals negative 3, so x is going to be plus or minus square root of negative 3, which is the same thing as plus or minus square root 3 times I. And then similarly, you can see that the roots here will be x equals plus or minus square root of 5 times I. Okay. So the zeros are going to be square root 3i minus square root 3i, square root of 5i, and minus square root of 5i. 1, 2, 3, 4 zeros. And then if we wanted to factor over the complex numbers, we just write, it's just going to be a polynomial x minus this number times x minus this number times x minus this number times x minus this number. So what this will look like will be x minus square root 3i, x plus square root 3i, x minus square root 5i, x plus square root 5i. Okay. And that's what this polynomial will become. Let's see, 8x squared plus 15, right? Okay. Okay. Every polynomial now finding the roots won't always, or finding the zeros won't always be this easy, but that's what the fundamental theorem of algebra says it's possible. Okay. And congratulations for making it through this very, very important lesson.